Ladies and gentlemen, it's my great pleasure to present some recent results about the Kepler system. We called this Kepler Fast Track since we are aiming at enabling a faster implementation of the system. This is joint work with Grzegorz Michalak, Christian Trainotti and Gabriele Giorgi. Let me remind the main goals for Kepler. For users, we want to provide precise point positions within seconds. We want to monitor the signal in space error and raise an alarm whenever it exceeds a threshold. This shall happen with low delay. Both of these properties are essential for the further automation. We want to maintain backward compatibility of services and also achieve some properties for the operator, minimize the extent of the ground segment to as little as 2 monitoring stations and minimize the reliance on atomic clocks and therefore increase the robustness. Next, I need to shortly summarize the concept of Kepler. We use the orbital slots of Galileo, we see one orbital plane here, and successively replace the Galileo satellites by Kepler satellites. In the initial phase, there will be dual mode Kepler-Galileo satellites. The Kepler satellites carry stable oscillators rather than clocks. Satellite navigation is about synchronized satellites. The synchronization is achieved by using two-way optical intersatellite links. They are used to synchronize the time and also to measure the distance, ranges. Furthermore, they are also used to transport information. The different orbital planes, the 3 orbital planes, may be connected via a layer of LEO satellites. So we have optical links through the LEO satellites, but also in different ways. Very importantly, those LEO satellites are equipped with L-band receivers. This is used for the calibration and also to provide integrity. The LEO satellite might also carry some long-term stable clocks in order to provide resilience to the system. 2 ground stations ensure that Earth rotation and the orbits of the satellites stay aligned. Furthermore, we also need to keep the timing system established by the satellites and UTC aligned. This is achieved by 2 stations receiving L-band signals. The main goal of Kepler Fast Track is to simplify the system to enable an early implementation without losing much navigation performance. We consider 3 elements. The first one is to replace the ultra-stable optical reference by an ultra-stable RF reference. The second element is to use a simple long-term stable clocks on the LEO satellites, or maybe none at all. And the third element is to reduce the number of optical links on the LEO satellites. In order to understand this last point, we have to look at interplane connectivity. Originally, this was established through the LEO satellites, which would connect to at least 2 planes. An alternative is to directly connect the planes via the MEO satellites. This doesn't involve the LEO satellites at all. so there is 0 terminal needed on the LEO satellites. This provides new options for simpler LEO satellites. A consequence of the present study is that both simpler options don't have an influence on the precise orbits of the MEO satellites. Since the rightmost option with no terminal does not provide calibration support and leads to a less performant integrity assessment, the focus is actually on the central one. The original Kepler system builds on an ultra-stable optical reference. The stability of that reference is translated into a modulation domain using a frequency comb. The two are phase locked and therefore provide very high resolution for the transfer of time and frequency. Unfortunately, the optical reference and the frequency comb have not yet been space qualified. In the fast track concept, we therefore built on an ultra-stable quartz oscillator in the modulation domain. So stability is established directly there, while the optical carrier is maintained as a transport capability for that modulation. In order to verify the capability of both systems, we implemented two transceivers, which we use in our indoor test range and on an outdoor test range. Our outdoor test range is between Weilheim and Hohenpeißenberg and has a length of 10.4 kilometers. We see here Weilheim from the Hohenpeißenberg. This work was performed by our colleagues Yanis Surov, Raphael Wolf, Luca Macri, Juraj Poljak, and Ramon Matacalvo. It will be published elsewhere. They set their power levels so that they would match the typical intersatellite distances of roughly 20,000 kilometers. The Hadamard deviation for the time transfer in the lab and on the test range is in both cases somewhere between 2 times 10 to the minus 13 and 5 times 10 to the minus 13, which is an extremely good value. This is a type of stability that we observe whenever we compare clocks of different MEO satellites. Most clocks are processed in a Greenhall Kalman filter, which produce an implicit ensemble mean. The difference between the local clock and the ensemble mean is used to create a local realization of this implicit ensemble mean. It's actually by using the difference with the local clock, let's say satellite 1, and the input from satellite 1, we can estimate the implicit ensemble mean in the Kalman filter and through a regulator control a combined NCO direct digital synthesis system to create this implicit ensemble mean realization. Kepler system time is implemented by a realization of the implicit ensemble mean on every satellite. We have simulated this for a system consisting of 24 MEO satellites, 6 LEO satellites, each of them equipped with an ultra-stable oscillator. All MEO satellites being connected by optical intersatellite links. For the LEOs, we have either 0, 1, or 3 optical intersatellite links connecting the LEO to the MEO. We have 1 active hydrogen maser on the ground representing UTC, which is connected by an L-band link. The measurement noise of the optical links and of the L-band links is given here. The result looks as follows. We have the overlapping Allen deviation of the different USOs in green. We have the corresponding quantity for the active hydrogen maser in blue. We have the implicit ensemble mean in dashed blue, and we have the realizations of Kepler system time on every satellite in black. We see that we achieve an excellent stability of that Kepler system time. Since we now have a specific implementation of Kepler system time on every satellite, we have to look at their difference, which is shown by this dotted curve. We see a degradation for small values of tau of a sampling interval due to the use of different USOs on both satellites, and we see in the long term a 1/tau decay, which provides an excellent capability to compare time. This concludes the discussion of time, and I want to switch now to discussion of orbits. I would like to remind you that we have three possibilities: three optical intersatellite links to MEO satellites, one optical intersatellite link to MEO satellites, or none at all. In precise orbit determination, we must first simulate the orbits and then estimate them. And here we use different models for a number of influences: gravity field, solid earth type, tides, ocean loading, and so on. We use one model for the simulation and another model for the determination. In the simulation, we use the EPOS software of Geoforschungszentrum Potsdam, and we are very grateful for being allowed to do that. We simulated a number of scenarios ranging from full Kepler to Galileo with 18 ground stations. The number of ground stations for all Kepler scenarios is 2. And 3 of the scenarios are fast track. One is the full Kepler. In the case of Kepler, the GNSS antenna phase center offsets need to be calibrated. And we see that actually the radial error is quite similar for all of the Kepler scenarios, for the full and the fast track, and clearly better than for Galileo with 18 ground stations. The C3 Galileo is performing quite well because it is absorbing some of the errors into the clock, and this is good for the precise orbit determination, but this is more problematic in the case of prediction. Actually, the results shown here correspond to a post-processing situation, and they are the basis for predictions. For prediction, we have to consider 3 elements. The first one is the clocks. The Galileo passive hydrogen masers are very stable and can be predicted by linear extrapolation. Kepler, there is no prediction because we have permanent synchronization. For the predictions, we assume that we know the models perfectly. We only have to estimate the parameters of a model. Galileo is capable of absorbing modeling inaccuracies in other parameters, mainly in the clock. Kepler, on the other side, due to the optical ISL exposes any form of mismodeling and allows to iteratively improve the estimates to near perfection. In the case of Kepler, the nonlinearity of Earth observation is the main cause of prediction errors in the orbits. Irregularities in the direction of a pole, like occur here, here, and here, and amplified in this curve, are unfortunately a problem. They also occur in the length of the day, a similar situation. They are associated with a prediction error, which in turn causes an error in the prediction of the orbit. This is shown here for Galileo with 18 ground stations, estimation, prediction. For Kepler with 2 ground stations. And in the same graph for both systems, we see that Kepler clearly outperforms Galileo, in particular in the radial direction. The prediction error in the case of Kepler is mainly due to the ERP prediction error. Without the latter error, the orbits can actually be predicted over several days. But even over one day, the CISRE of a prediction for perfect models of Kepler compares very favorably with the corresponding value for Galileo. Let me now come to my summary and conclusions. The fast track is a simplified concept of Kepler, which can reach a high technical readiness level much faster than the original approach and also reduces the operational risk in an initial phase. The precise time transfer capability was demonstrated in the lab and on our outdoor test range. We have an excellent level of synchronization, which we obtain from simulation of system time. We have different options for the LEOs, and they all perform very well in terms of precise orbit determination and orbit prediction. And we have a very low CISRE of the predicted orbits, which are obtained by simulations. Now, the next steps are, first of all, we have a mission for on the ISS, the Compasso project, where we want to test the original and fast track approach. Besides this, we aim at the validation mission for the fast track approach in MEO orbit. And in parallel to that, we are preparing detailed simulations of the complete system in which we can experiment all types of scenarios, also scenarios leading from Galileo to Kepler in successive steps. Thank you very much for your attention.